Are you ready to give a more detailed presentation?
Yes, I do. Provided this works. Well, yes, so this brings me to the 4th of July 2012, which is a date that marks a new era in particle physics. And this is not only because François Englert and Peter Higgs met for the first time ever in front of a packed auditorium at CERN, but mainly because their ideas on mass of the fundamental particles had just been confirmed. But let us start by going 50 years back in time. In the autumn 1964, Englert, together with Robert Brout, who is now no longer with us, and Peter Higgs independently published 2 manuscripts explaining how certain particles can obtain mass. As you can see, the publication dates are only a few months apart. In the case of Higgs, October 19th. In the case of Englert and Brout, August 31. So both made a contribution to explaining the origin of mass, and these contributions cannot be distinguished. Now, what they did is central to the so-called standard model of particle physics. And let me try to explain what the standard model of particle physics is about by taking this example of a fly. So everything around us, and we ourselves, flowers, trees, stars, can be described in terms of a handful of constituents of matter and the forces acting between them. And so if you now look at the fly, it consists of molecules. Each molecule consists of atoms, and each atom has an atomic nucleus, and orbiting around the nucleus we have electrons. Nuclei are not fundamental particles. The protons and neutrons have in turn fundamental constituents which we today believe are indivisible, and they are called quarks. Now, these fundamental matter particles interact by means of forces, and within quantum mechanics we believe that these forces are mediated by quanta, by particles. And so we have the electromagnetic force mediated by photons, which are massless. We have the weak nuclear force mediated by massive particles, which are called W and Z, and we have the strong nuclear force mediated by massless gluons. Now, all is well and good, except that the theory behind the standard model would like all the mediator particles and all the matter particles to be massless. Now, here is the standard model of particle physics as we know it, with the matter constituents on the left-hand side, the quarks we've been talking about, the electrons, which you all know, part of the atoms, and the electrons' cousins, the green particles. On the right-hand side, we have the quanta, which mediate interactions between these particles, the Z and the W of the weak force, the photon, which we all know and love, and the gluons. And the theory would like all these particles to be massless. However, we all know they are not massless. I mean, we are not massless, unfortunately for some. So something must be there in the background to give these particles mass, and this is symbolized by this gray cloud in the background here with an H on top. So how can the world be so diverse? What is the origin of mass? Now, the problem is that to make the standard model work, we need theories which are basically symmetrical. But these symmetries forbid particles to have mass. If you try to put in mass by hand into the theories will collapse, and the standard model no longer works. So somehow the symmetries must be broken in such a way that keeps the good properties of the theory. Now, this is where the Mexican hat comes in. And I believe that everyone has seen this picture of the Mexican hat. Now, the Mexican hat symbolizes asymmetry. If you think in terms of a hat, you see a hat in front of you, and suppose you had the bag which sits on top in the center of the hat. To you, all the world looks symmetric. All directions are equivalent. However, if you slide down into the valley, then the world is no longer symmetric. There's obviously one direction in which it's easy to move, which is around the center, and there are directions in which it's difficult to move, and it's up and along the brim. And so now we have a situation which was symmetric to begin with, but which is no longer symmetric. Now this Mexican hat symbolizes, illustrates a piece of mathematics that Dra Olga and Higgs added into the theory to show that you could have a theory which was inherently symmetric, but where the ground state, the state of the lowest energy, did not display this symmetry. And this is what saved the Standard Model. Now, the theory made a concrete prediction, namely, 1, there should exist a new fundamental particle, and 2, all the other particles in nature, the matter particles and the quantum mediating forces, should gain mass through interactions with these particles. Which brings us back to the 4th of July 2012. Appearing in front of a packed auditorium at CERN, the spokespersons of the experiments Atlas and CMS announced the observation of a new fundamental particles in proton-proton collisions at the Large Hadron Collider, which had properties consistent with the long sought-after Higgs particle. And you can imagine that the whole auditorium exploded in applause. Now here you see, again, Higgs and Englert waving to the auditorium after the announcement of the observation had been made. Now, what I'm going to show you is what the evidence for the existence of a new fundamental Higgs particle looks like. This is a little bit difficult, so I ask you to have a little bit of patience. So we have a diagram here showing on the horizontal axis the mass. Okay? Now the Higgs particle cannot be seen directly. It can only be reconstructed from its decays, from traces it leaves in particle detectors. So from these traces you can reconstruct the particle mass, but it is not clear it comes out exactly in one point. You can get many different masses. So on the horizontal axis you have the reconstructed mass. On the vertical axis you have the number of events found at each mass. There is another caveat, namely their background. There are processes mimicking the Higgs, which are not the Higgs particles. They are not the processes you're after. And they will be shown in blue in this diagram. So what you are going to look for is the red peak appearing in data against the blue background. And I'm going to show you how the data evolves with time. The black points will be data. And so look for the red peak and try to follow the time development. So here you see it comes up as more and more data are collected. You see the blue background growing fast, but also the small red peak appearing. And this is the observation of the Higgs particle. Now this is not the data they had in 2012. Now I'm showing you all the data we accumulated until the shutdown of LHC in the beginning of 2013. So I think I can stop this. This is what the data looks like. We see the red Higgs peak on the blue background. And so what we have here is the final piece in the puzzle, which is the Standard Model. This is, of course, not the final piece in the puzzle of the universe. There's still mysteries left. We don't know what the dark mass is. We don't know what the dark energy is. We don't know if Higgs is the only Higgs particle that exists or if there's more Higgs particles. So obviously, there are things to do for future generations of scientists. Thank you.
Thank you, Professor